Thank you. We are very excited to be here, and welcome to our talk about practical functional programming in React. I don't know. So my name is Dafna. I'm a tech director at ApeGroup Sweden, and I'm passionate about clean code and engineering culture. And I have a blog in Medium about technology, and I also created with Netta a podcast for developers called Extend.
Netta is me. I am a front-end developer in Tikal here in Israel. I also blog about technology. And I was going to tell you about Baot, but Adam already did it. So let's skip to tell you about our talk. So today what we want to do is cover some basic concepts in functional programming. So we're going to talk about referential transparency, denotational semantics, compositional functions. No, it's okay. I'm just kidding. Breathe. We're going to cover these, but what we really want to talk about is sticking them with the pointy end. That means straightforward, practical things that you guys can do in your React apps today to make them more functional and get the benefits of functional programming, which include things like reduced complexity, more declarative code, better testability, and so on. So I want to start by talking about the two basic building blocks of functional programming. These are pure functions and function composition. So pure functions are functions that live up to three conditions. One, they have explicit inputs. That means all of their inputs are expressed in their parameters. Number two, they have explicit outputs. So all of their outputs are expressed in their return value. And number three, they have no side effects. So they don't affect anything outside of themselves. So that's one part of functional programming. And then the second part, the second building block, is function composition, which is how we combine functions together. So the way that we construct logic in functional apps is through function composition, which means combining functions to create more complex expression. And when we do that, we want to maintain something called compositionality. So compositionality is a principle that means that the meaning of complex expressions should always be determined by two things. Number one, the meaning of their parts. In our case, we're constructing logic out of functions, so these basic parts are going to be functions.
What is the meaning of functions? Is that 42?
Well, the meaning of a function can be 42. So when we talk about the meaning of a function, we're talking about this characteristic that pure functions have, that for the same input, they always return the same output every time. And because of this, if I know their input, I can always know their output value, and then technically, I could replace the function with its output value. So when I'm talking about the meaning of functions, I'm talking about this deterministic value that pure functions have. So this is one thing that determines compositionality, and then the second thing is the rules used to combine these functions. And what this essentially means is that if I want to understand any complex expression, what I need to do is break it down to its smallest parts and the rules used to combine them. And if I know both of these things, I can know the meaning of the whole. Now, if you can imagine building all of your software with this principle in mind, think about how easy to understand that software would be, because all I would have to do is break it down to its smallest parts and the rules used to combine them. So software that is built with compositionality is very easy to reason about, and it's very easy to debug, which is why we want to make sure we maintain this principle. So we want to look at three ways that we can maintain compositionality in JavaScript apps, and we're going to give some examples from this demo app. So as you can see, in keeping up with our theme, we have a list here of the Stark family members. And for each of them, we have some information. Did anybody not watch season 8? No, I think it's going to be okay. So for each of these Stark family members, we have some information about them. So some of them may be alive, and some of them are unfortunately dead. And then based on their state, I can do different actions on them. So if they're alive, I, as the omnipotent creator of the app, can decide to kill them. And if they're dead, I can decide that I actually didn't mean to do that, and I need them back to further the plot, and then I can resurrect them. And I do that with these actions here. So for example, if I decide that Arya Stark has had her share of brushes with death, and I think it's time for her to go, I did not expect such strong emotions. Okay, so I can kill her, and then you see her state changed, and also the actions available to her changed. And if I want to resurrect, for example, Catelyn Stark, then I can resurrect her, her state changes, and the actions available to her change as well. Now, there's one more very important feature I've added here, which is at any moment in time, I can decide that one Stark family member is the absolute worst Stark. At the moment, this honor is reserved to Bran, but I'm willing to have this discussion. So if you guys feel like there's somebody else who should be the worst Stark, now is the time to shout it. No, somebody has to shout really loud so I can hear them. I'll go with Rickon. That I can go with. So if I decide that Rickon is actually the worst, then I can click this button here, and you see his state changed. And the important thing is the actions available to him changed. And so there's some kind of logic governing which actions we show here for each character, and we want to use that to see how we construct that logic in a functional world. So let's look at 3 ways that we can construct logic using pure functions and composition and maintain compositionality. The first one is basic composition. This means I apply a function to the result of another function. In this case, I call function A with an argument, it returns a value, and I apply function B to that argument. This is pretty straightforward and very easy to reason about. However, it has a very obvious downside, which is I can do this twice, maybe 3 times. But any more than that, any more functions, if you imagine like 6 function calls, it'll become a lot more complicated and a lot less readable. Then another way I have of maintaining compositionality is currying. What's happening here is I create a function that takes an argument, argument A, and it returns a function that takes another argument, argument B. Then in the body of that final function, I have access to both these values, and I can do something with them. And the way I'll use this is when I get the value of argument A, I'll call the first function and pass it some value, say 1, and I'm creating a closure here over that value. And then when I get the value of argument B, I can call this function I created and use both A and B in my calculations. The way this would work in a real-life app is something like this. So you remember I have all of these actions, and I have a different subset of actions for every character based on their states. So I want to be able to filter those actions for whatever type of action I want. So for example, I can decide to use this function to filter for the kill action, and I then create this kill action filter. And then I'm going to...
It looks a little complex. Why is it better than just passing 2 arguments to the function?
Daffy said it's very complex. She's not wrong. But I'll tell you what is the benefit of this method. Then there's 2. One is, imagine I have a really large app. I'm showing all of the families in Westeros, and I want to have all of these different actions available for all of them. I can use this one function to create all of my filters. Kill filter, resurrect filter, marry filter, whatever else I want. And I'm creating these small units of logic that are very, very declarative. It's very obvious to me what the kill action filter function does. Then the second reason I might want to use this is if I'm getting the values at 2 different times. So if I have access to the action type first, and I'm waiting for the action array to return from the server or something like that, then I can use currying to sort of speed up when I do things. So this is currying, and currying also suffers from a similar problem that we saw before, which is I can curry for 2 levels, 3 levels. After that, it becomes a lot more complicated. And what I really want is to have some sort of mechanism where I can just compose as many functions as I want, maybe even an undetermined number of functions. It turns out that if we're looking for inspiration for such a mechanism, we can look to another JavaScript, functional JavaScript library, which is rxjs. rxjs has a pipe method, which looks something like this. I'm creating a pipeline of functions. And the way this works is my argument will be passed to function A. Whatever is returned from that will be passed to function B. Whatever is returned from that will be passed to function C, and so on and so forth.
It looks really similar to the first example that you showed.
It is very similar. In fact, behind the scenes, it works exactly the same, right? I'm calling each function with the value returned from the one before. However, it allows me to create this readable, declarative, clear syntax and build these function pipelines. Now, you can't use rxjs to pipe regular functions, and you definitely don't need to bring it into your project. We can actually build a pipe function quite easily in vanilla JavaScript. This is, in fact, a simplified version of the rxjs pipe, and if you guys are interested in that, you can go look at this file in rxjs. So what I'm doing here is I'm using currying to create this pipeline. First, I create a function that gets any number of functions as parameters, and it returns a function that takes a single argument. Then in the body of that function, I use reduce to iterate over my function array and call it each time with the return value coming in from the previous function. And so this helps me, the way I'll use this is with this same syntax that we saw before. Now, it's important to keep in mind here that the best, easiest way for me to use this would be if each of my functions return the same type of value. So technically speaking, I could return different values and then keep track of what function returns what and what function takes what as an argument. But if I just return the same value every time, say an array, then this becomes really, really easy to reason about and work with. And there is one use case where I think this could be very helpful. It's a bit of an edge case. I'm sure none of you have ever run into it. This is probably a problem only I have. But sometimes you get data from the server not in the format you need it. And in that case, it can be helpful to build this pipeline that will help you format the data and do some operations on it, some data manipulation. So for example, in my app, I've prepared this pipeline where I get my data from the server. First, I parse it, and then I attach the relevant actions to it. And the way I use this is I create this pipeline early on, and then when my response returns, I call this format family function with a response from the server. So we've looked at 3 ways to compose functions and maintain compositionality. That's basic composition, currying, and piping. And these 3 ways are, I think, really easy to implement in any JavaScript app, and they will help you maintain compositionality and get those benefits of easy to reason about, easy to debug code.
That's really cool.
We are
Thank
switching.
you.
Oh, yes, and less complexity.
OK, cool. So let's look at other ways that we can make our React app more functional. I was really curious to see what's functional about hooks or what functional patterns hooks allow us to use. And I think I have some really cool findings that I'll share with you in a minute. But before that, 2 things. First, I'm not going to get into the details of the syntax. I'm going to assume that you already encountered hooks. And second, I'm not going to use Game of Thrones examples because I didn't watch or read the book. So the first thing to know about hooks in this context is that they encourage us to use function components instead of class components. And before we had hooks, we could access the state and lifecycle methods only from classes. But now we can access it also from function components, and it allows us to avoid using inheritance and think in a more functional way. So let's look at this example. We have here a counter, and every time we click the button, we increase the counter. So every time we set a new value to counter, the component re-renders. And on every render, the component sees the counter as if it was a constant. So let's say we do a long operation and the state changes while this operation is running. Inside this operation, we will still see the previous state. And that is different from classes, because this .state.counter in classes will always point to the latest value. There is something we can do using hooks to see the latest value, but it might imply the wrong design. So let's look at our handle click function. We actually do two side effects in it. When we read the counter, it's a side effect because we don't get this argument as an input to our function. It's some variable that exists outside of this function scope. And when we set the counter, it's also a side effect because we update something external. So there is one improvement that we can do, and is instead of passing a value, we can pass a pure function. And we can calculate the next state from the previous state. But in the second example here, we still do side effect because we still set counter, which is a side effect. So what we can do if we want to make this function pure is to pass the setter from outside. Now, it's not something that we always want to do, but it helps start thinking in a more functional way and think about our functions in terms of side effects and pure functions. OK, let's talk about side effects. So we have a new hook called useEffect, and it helps us to separate our code to side effects and pure functions. And side effects can be, for example, calling an external API or updating the state. And we have to have side effects in our app. We can't avoid it. I mean, even Haskell applications have side effects, and especially front-end applications where we update the DOM. But what we can do is to separate them and divide our code to side effects and pure functions. And it will be much easier to test our pure functions and to understand them. So let's look at this example. It's a GIF, so you can see what it renders on the top right. And we call useState and useEffect, and inside useEffect, we set a timeout, and we increase the counter by 1 every second. And we also, in this case, return a cleanup method. So let's talk about the order of operations happening here. useEffect does not block the rendering. So the first thing that will happen is that it will render for some state, x. And then the second thing is that the cleanup method for the previous state, x minus 1, will run. And then the third thing that happens is that the effect for state x, the current state, will run. So because it does not block the rendering, it really allows us to use side effects inside useEffect, because we can do some heavy operations. Now, let's look at this example. So as I said, useEffect will run on every render, and it's not something that we always want. In this example, we can see that we set some timeout, and inside it, we update the counter every 5 seconds, so increase it by 5. But we also have another counter, a counter that we increase every time we click a button. And we don't want to set our timeout every time we click the button. So we want this effect that we see here to not run on every render. And the way we can do it is by adding a dependency array. So it's going to be a second argument that will give useEffect, and inside it we'll put only the dependencies that we're going to use inside that effect. And every time we re-render the component, React will compare the two arrays. And if they're different, it will run the effect. And if they're the same, it won't run the effect.
Wait, so what do we need to put inside the dependency array?
Great question. So we have to put inside the dependencies array all the props, all the state parameters, and all the functions that we're going to use inside useEffect. Let's say we have some long logic that we want to run inside useEffect. Or maybe we want to reuse it across different effects, because we can have more than one effect in our component. We can have as many as we want, let's say 3, and inside each one of them we can have separate logic encapsulated. So because this effect is running instead of component did mount and component did update, now we don't have to put unrelated logic inside the same function. So let's say we extract our method because we want to reuse it by other effect. And now we have external method set timeout setter, and we use some state inside it, so we have to put it in our dependencies array. And that causes a problem, because this function will be created from scratch every time we render the component. And that makes the dependencies array redundant, because its entire purpose is to help us not run the use effect every time we render. What if in our extracted function we don't have any state or props? In that case, we don't have to put it in the dependencies array, but it's not the best practice, because maybe someone later will add state or props to it, and then it's hard to identify that we actually need to add it to the dependencies array. And it might cause some consistency bugs, because we will see some previous state. So luckily, there are 3 solutions to this problem. The first one is to use a hook called useCallback, and we will wrap our extracted method by it, but it complexes our code. And what's interesting is that the 2 other solutions have some functional aspects to them. So the second thing that we can do is to take our extracted method and put it entirely outside of the component. And this way we can make sure that it won't have access to the state or props. So we actually turn it into a pure function. And the second solution is to use a hook called useReducer. So this is a reducer function, and it's pure, so it's very easy to test it and to understand it. And if you worked with Redux before, which I assume you had, you are very familiar with this pattern. And in some application, useReducer can replace Redux entirely. And it's really nice, because the less libraries, the better.
Wait, Duffy, sorry, I choked on my water. But I wanted to ask, so is useReducer the same as Redux? Does it store app-level state?
Well, in some, we can use it actually in 2 different ways. So the syntax looks like that, as you can see. We call useReducer, and we pass a reducer function and some initial state, and we get back the state in a dispatch method that we can then call and pass some action and update the state. And we can pass this dispatch method throughout our tree of components, and then call it from some other component, and it will update our state. So in that sense, yeah, it's global. But we also can just run useReducer another time again, and give it even the same reducer and the same initial state, and we'll get dispatch 2 and state 2, and calling dispatch 2 will update state 2 and not state. So now let's compose.
Don't drink. It's a trap.
I did it. OK. Let's think about compositions with hooks. For example, useEffect. We run it, we use it so that the code inside it will run on every render. So if we want to run useEffect inside useEffect, it doesn't really make sense, and it won't help us to do anything. But if we look at the implementation of useEffect, it actually receives a function. So the implementation itself of useEffect is functional. And what we can do is to pass it a carried function. And this is how it will look like. So we have here a carried function, update count, and it receives a setter, current, and increment as 3 arguments. And it returns a function that sets the timeout according to the input arguments. And you can see below how we compose them together. And the other composition that we can do is using custom hooks. So we can take useState and useEffect, or any hook that we want, and use them outside of our component. So we can actually take this code and just paste it in an external file and call it from every component that we want. And that's a new way to reuse stateful logic that we can use instead of higher order components and render props. So what happens if we have another effect that we want to do? For example, to write to log. And we want to do it right after we run our custom hook. What options do we have? So the first thing that we can do is to add this effect inside our custom hook. But that way, we won't be able to reuse this code. So another thing we can do is to create a new custom hook. And we can call it from the previous hook. But that way, they are coupled. So maybe if we change one of them, we'll have to change also the other. And that's not ideal. So the third solution is to compose them. And this is how it will look like. On the left, we have useCountTimeout hook, which we saw 2 slides before, custom hook. And on the right, we have useLog custom hook. And it receives some hook and runs it and saves the result, and then logs it and then returns the result. And you can see below how we compose them together. So to summarize this part about what's functional about hooks, I found 3 main things. The first is that we now can separate side effects and pure functions, and it allows us to think in a more functional way. And the second is that we can compose custom hooks. And the third is that we can manage our state in pure reducer functions with useReducer. And to summarize this whole talk, so JavaScript is not a functional language per se, but there are patterns that we can use to make our code more functional, and by that, more readable and more testable. And it doesn't have to be only by using libraries like Lodash. We can think in terms of pure functions and side effects, and we can compose our functions and so on. So we hope it gives you some food for thought.
So thanks, guys, for your attention. If you have any questions, if you want to discuss something, if you want to argue, we're around. Feel free to come find us, and you can also DM us on Twitter, where we will be posting this presentation soon. Thanks.